All right, now we move on to lesson 4 of exponents, and this is negative exponents. So negative exponents, we've actually lightly mentioned these before, and we've kind of dealt with them, but now we're going to really formalize it here. So let's consider our first example here, or the first piece here. If I have 2 to 4 to 8 to 16, I see that there's a pattern of these numbers being multiplied by 2 in order to get to the next step. The next step is always multiplying by 2. Now, if I want to represent this in terms of something to do with powers, well, I would say, okay, well, 2 to the, if there's nothing written, this is a 1. We have 2 to the 1, 2 to the 2, 2 to the 3. By that sheer pattern of 1, 2, and 3, I can assume that this is going to be 2 to the 4, and this is 2 to the 5. And if you were to type these into your calculator or even just expand them, you would know 2 to the 4 is equal to 16. And then 2 to the 5 is equal to 32. So that is something you can directly confirm. Now, if I go a little bit right here, we say, okay, well, if we knew that we multiplied by 2 and the end value was 32, what if I work in the reverse direction? And I'm going to try and show this through powers and then go back to our numbers here. So if I'm working in the forward direction, we knew this was 2 to the 4th power, this is 2 to the 5th power, and we knew 2 to the 4 was 16, 2 to the 5 was 32. But if I know that this is to the power of 1, what is the 1 power that's going to be to the left of this? Well, if we know in the forward direction we're adding 1 to each of the exponents, in the reverse direction we're going to subtract 1. So this becomes 2 to the 0. And by this, we know 2 to the 0 is always equal to just 1. So if you would like to, you could actually just write that this is also equivalent to just 1. And then if I subtract by 1 more, I have 2 to the negative 1. And what we're going to come to realize is that this is actually the equivalent of writing 1 over 2 to the positive 1. And we've lightly covered that in the previous lessons, but here's what we do with them. We drop them to the denominator, see that negative, and we drop it. Now, what does this mean? Well, our value in the box here is when we divide 2 by 2, we get 1. And then if we divide 1 over 2 by another 2, or we divide it again by 2, I should see that I have 1 over 2, and then the pattern would continue and I would get 1 over 4. We continue to divide by 2. So if in the forward direction I'm multiplying by 2, and then in the reverse direction I divide by 2, I should see that the reciprocal is just on the left-hand side, it's the same as the right, it's just the reciprocal of it. So let's actually do some direct examples. Before we do that, what I would like to do is just highlight specifically the definition of what a negative exponent is doing. So suppose if I have a to the negative m, well, it's going to flip and become the reciprocal 1 over a to the positive m. If I have 1 over a negative m, this is going to flip and become the reciprocal and say I have a to the positive m. So if we have a negative exponent, well, to make it positive, we move it from the numerator to the denominator, or if it's in the denominator, we move it from the denominator to the numerator to change signs. Now, this is no different than if we had a rational number. So suppose this a over b is rational, which we denote by q from number sense. Suppose this a or b is rational. Then what we can do is we can say if a to the negative, or an a over b to the negative m means that we have a distribution of this, let's show that we can actually get to our step of b over a to a positive m. So below, I'm going to set this equal to, by distribution rules, if I go from here to here, we know that the negative exponent will distribute and become a negative m over b to the negative m. And that's by power rule. We just multiply it into the brackets. Well, what do we know? We know a negative will always flip it to the opposite location and make that exponent positive. So I can rewrite this as bm, b to the positive m. That negative m has been relocated, or the base b has been relocated and made a positive exponent. I'm going to do the same thing with a. I'm going to relocate a and make it a positive exponent in the denominator here. All right, and then if we know that they share the same exponent, I can actually directly remove this out of the brackets and say b over a and move my m outside of the brackets, because by power rule, that m could be redistributed back in to the b to the 1 and the a to the 1 and become the previous step here. So the big thing with negative exponents is that it doesn't flip the exponent, it flips the base value. And so if you wanted to write that as a note, we know a negative exponent, it's going to flip the base and not the exponent. Really important notice there. All right, let's try some examples here. I'm going to go to A here. We know a negative exponent will flip the base to the reciprocal of wherever it is. So in this case, it is in the numerator. I'm going to flip the A to the denominator. And what do I do with the exponent? It becomes positive. If I go to B here, by power rule, what I can do is I could distribute that negative 3, or I can realize that 1 over 3x is the reciprocal, and this is to the power of positive 3, and now I can expand this through. If I expand 3 to both of these terms, well, 3 to the 3 is going to be equal to 27, and then x multiplied by the cube will be x cubed. All right, I go back to part C here. A negative means that this can be distributed and that I know that the two values or any value that's connected to this exponent will flip and be the reciprocal. So I'm going to show it kind of two ways here. I could immediately just flip this and say I have 3 over 2 to the positive 4. And then I can distribute my 4 and say I have 3 to the power of 4 over 2 to the power of 4. Or what I could do is I could say this is equal to, I could have 2 to the negative 4 over 3 to the negative 4. And negatives mean we relocate to the opposite side of the fraction. This means I have 3 to the positive 4 over 2 to the positive 4. So either way you want to do it, you can distribute that negative exponent and then flip, or you could flip the entire fraction and then apply the exponent. You will get the exact same solution here. All right, I'm going over to D here. So we have a quotient scenario, and yet again, this can be solved two ways. I have x9 over x to the negative 2. I could solve it like this. By quotient rule, I subtract 9 minus that negative 2, and I have y 6 minus the 8. This means I have x9 minus 2, which is x to the 11th power, times y to the negative 2, which means then I would relocate the negative 2 to the denominator and make it positive. The other way I could do this is say, what if I set this equal to x to the 9, I relocate the negative right away to my numerator, times y6 all over y to the 8. This means I'm going to have x to the 11 and then y to the negative 2. I relocated x to the 11 over y to the 2 as such. So you can either relocate your negatives right away, or you can just use standard rules and subtract them by quotient rule. That would also be acceptable. So as you can see, there's going to be multiple ways to do these problems, and there's no set right way in these regards. All right, I'm going to go over to E here. E, what I can do is I can flip them all. And so maybe for this example, what I'll do is just show the one way of me flipping everything and then solving. So if I flip everything that has a negative exponent, that means my a2 becomes a positive in the numerator. My b to the negative 2 in the denominator becomes b to the positive 2 in the numerator. I have a b6 that was in the numerator, and it's positive already, so I'm going to leave that behind. And then I'm going to flip the 2a cubed that was all to the negative 2 and make this all positive here. So by product rule in the numerator, I can combine the b's and say I have a squared common base and add 2 plus 6, which gives me 8, all over I can distribute my squared to both terms here and make this 2 squared and a to the 3 times 2, which is 6. My next line of simplification would be a squared b8 all over 4a6. And now I realize I have a quotient rule here of a2 over a6. This is going to be equal to a to the 2 minus 6, which is negative 4, b8 all over 4. And I know I have to relocate my negatives. When I relocate my negatives here, that's going to be b8 over 4, a to the 4. Now here's something I'm going to do on the side here. We know we had that a2 all over a to the 6. I challenge my students and I say, or I challenge the students and say, in this case, where are the a values greater? Where is there more a's? And the correct thing would be to say, well, we have a to the 6 here, a to the 2. That means there's a greater amount of a's here because I have a to the 6 rather than a to the 2. So by sheer prediction, we should know, even if we do quotient rule and show it that way, the a's should eventually be in the denominator. But in this case, I can teach you a shortcut that you can use to confirm your solutions. Well, if I have a greater amount of a's in the denominator than the numerator, how many is it greater by? Well, in this case, it's greater by 4, meaning that's my solution. I can say 1 over, and when they combine, wherever it's greater, you're writing the base. And then how much is it greater by? In this case, 2 minus 6, that's going to give you a value of 4. All right, and then finally, we have our example F here. We have 14a to the negative 5 divided by 7a, 2a to the negative 4. Remember, our first check is always saying, if we have brackets, can we combine anything in the brackets? Well, in this case, we actually can. This is going to be equal to 14a to the negative 5 divided by 7 times 2 is going to give me 14. A to the 1. We know this exponent is a 1 here if it's not written. A to the 1 times a to the negative 4. I keep the common base, add the exponents. 1 minus 4 gives me negative 3. And now what I could do is I could create a division statement that's vertical. So I could say, well, I have 14a to the negative 5 over 14a to the negative 3. Well, we know that 14 over 14, that would reduce to 1. And a negative 5 over a negative 3, here's where I challenge you and I say, okay, well, where is the a values more positive or closer to 0? Which one is the most positive out of these a's? Is it a negative 5 or is it a negative 3? And what you should be thinking is, oh, well, negative 3 is closer to 0 than negative 5 is. So where are my a's going to belong? They're going to belong in the denominator. And then I'm thinking, what is the difference between negative 5 and negative 3? The difference between those numbers is 2. So therefore, I can say I have 1 over a to the 2. Now by quotient rule, let's make sure we prove this to show it. This is going to be equal to, well, 14 over 14 is 1, and a to the negative 5 minus a 3, well, this is equal to a to the negative 2, and we know a negative relocates it, so it's 1 over a squared. So we've confirmed that we actually can get the same result using quotient rule or just using the logic behind this and saying which a or which variable has the greater exponent. Is it the one in the numerator or the denominator in this case? Well, negative 3 is definitely closer to 0 or more positive than negative 5. By how much? By a factor of 2, which we can confirm using quotient. All right, this is the Check Your Understanding. Go practice.